Hi, in this video I'm going to go through the Edexcel Chemistry AS paper. That's paper 1 and it's the 2018 paper, and I'm going to go through the second half of this paper. Did the first half in an earlier video. Okay, right. Chlorine and iodine are in the same group of the periodic table. Complete the electronic configuration of chlorine using SPD notation. Well, here's chlorine here. You can see it's in period 3. And it's in the P block, so it's going to be 1s, that's going to be full at 1s2, 2s2, 2p6, so the second shell's full. Then we've got 3s2, and then we've got 1, 2, 3, 4, 5, it's 3p5. Explain why iodine and chlorine have many similar chemical reactions, right? Because in the same group of the periodic table, they're both in group 7. They've got similar electronic configurations. That should get you the marks, but you may want to say, well, chlorine, the outer shell, you've got 3s2, 3p5, whereas with iodine, it's going to be not 3s, it's going to be 5s2, 3p, sorry, 5p5. So similar electronic configurations, so similar chemical properties. Okay. Members of the same group sometimes react in different ways. Iodine and chlorine react differently with thiosulfate ions. Iodine gives this, called the tetrathianate ion, whereas chlorine gives the sulfate ion. Complete the oxidation numbers of the 3 sulfur-containing ions. So we're going to use this little equation. The sum of the oxidation numbers is equal to the charge on a species. And we know oxygen has got a fixed oxidation number in all of its compounds, nearly all of them, of -2. And so sulfur is going to be variable here. So let's do the thiosulfate ion first. So we're going to get the charge on the species is -2. We've got 2 sulfurs, they're unknown. We've got 3 oxygens, each of which is -2. So that's -6 for the oxygens. Do a little bit of algebra. 2s is equal to +4. Divide by 2, S is equal to +2. S has got an oxidation number of +2 in the thiosulfate ion. All right, let's do it in the sulfate ion. Charge on the species again, -2, just 1 sulfur. We have got 4 oxygens here, so that's 4 times -2 -8. So S is equal to +6 for that. Finally, for the tetrathianate ion, this one here. Right, charge on the species -2. Each sulfur, we don't know, 4 of them, so 4s. And we've got 6 oxygens at -2, so that's -12. So 4s is equal to, take that 12 to the side, +10. Divide by 4, S has got an oxidation number of 2.5, which may seem odd to have a fractional oxidation number. And the reason why, the question doesn't ask you, but it's because you've got 4 sulfurs in that ion. 2 of them really got an oxidation number of +2, and the other 2 have got an oxidation number of +3. Okay, so that's that. Right, the equation for the reaction of iodine with thiosulfate ions is below. Right, it's stated in terms of electrons why iodine is classified as an oxidizing agent. Right, so oxidation is loss of electrons, so I2 makes this thiosulfate lose electrons. I2 removes electrons from that, and it becomes reduced itself to 2 lots of I minus, and obviously the I2 has gained 2 electrons to turn it into 2 I minus. It's removed those electrons. It's an oxidizing agent. Okay, use your answer to B1 to show that chlorine is a stronger oxidizing agent than iodine. Okay, well, let's look at the table. It says that iodine oxidizes thiosulfate up to the tetrathianate, which is +2.5. It oxidizes it up that much. Whereas if you look at chlorine oxidizes it from +2 all the way up to sulfate, which is +6. So it oxidizes it to a higher oxidation state. It's a stronger oxidizing agent. Okay, that's the answer to that one. And right, so chlorine reacts in aqueous solutions to give thiosulfate to give sulfate ions. The ionic half equation for the reaction of chlorine is there. Write the ionic half equation for the reaction of aqueous thiosulfate to give sulfate. Okay, so let's write that down. So we've got S2O3 2 minus, and that is going to go to SO4. Right, the first thing we need to do is balance for the sulfurs, because we need to put a 2 in front of there. Then we're going to balance for oxygen. So we've got 8 on the right. Sorry, that's 2 minus there. We've got 8 on the right and only 3 on the left. So that means we're going to need 5 H2Os here. We need 5 oxygens balanced with H2Os. Right, so that means we have got we've got 10 H's on the left and none on the right. So that means we need 10 H plus on the right hand side of the equation. Now let's do that. Now finally we need to balance the charges with electrons. So on the right hand side of the equation we've got -2. On the left hand side of the equation we have got 2 lots of -2 minus 4 plus 10 pluses, so that's going to be +6. So that means we have got to add 8 electrons onto the right hand side of the equation. Okay, and if you just want to check the oxidation numbers there, that's the right number of electrons, because that's each sulfur there's got a +2 oxidation state, each sulfur there's got a +6, so each one's gone up by 4 electrons, but there are 2 sulfurs, so that's why we need 8 there. Okay, and the next part of that equation, use your answer to B4 and the half equation for chlorine to write the overall ionic equation. Okay, now this one here is a 2 electron process, and this one here is an 8 electron process. So we're going to have to multiply this one by 4 before we add them together. So the final equation is going to be 4Cl2 plus thiosulfate plus 5 waters goes to 2 sulfate ions, 10H plus, and 4 lots of, so that's going to be 8 chloride ions. Okay, so there's the equation for that. Okay, the compounds hydrogen, fluoride, water, and methane all have simple molecular structures but different boiling temperatures. Discuss the reasons for the differences in the boiling temperatures. This is a big question, 6 marker. Of the 3 compounds, using the data in the table and the Pauling electronegativity values in the data booklet. So I've copied that in here. Okay, so let's look at hydrogen fluoride first of all, which has got, okay, right, let's look at hydrogen fluoride and water. Right, so we've got a big difference in electronegativity between hydrogen and fluorine there. So if we look at hydrogen is 2.1 and fluorine is 4. Okay, so that means the hydrogen fluoride molecule has got very strong partial negative charge in the fluorine and a partial positive charge on hydrogen. Right, that means this hydrogen is sufficiently delta positive to be able to form hydrogen bonds. Okay, so you're going to get hydrogen bonds forming between a lone pair on a fluoride on the fluorine atom and the strong partial positive charge on a hydrogen on a neighboring hydrogen fluoride. Okay, now so that means in HF you're going to get hydrogen bonds, which are the strongest kind of intermolecular force. So that means the boiling point is pretty high. It's 19 degrees Celsius, whereas compared to methane, which is way lower, minus 161. Now let's look at the situation with water. Water, again, we've got a big electronegativity difference between hydrogen and oxygen. If we look here, oxygen is a very electronegative. It's the second most electronegative element after fluorine, 3.5. It's a lot more electronegative than hydrogen, so you're going to have a strong partial positive charge on that hydrogen and strong partial negative charge on the oxygen. Now this can form hydrogen bonds as well, because this hydrogen is sufficiently, so the partial charge is sufficiently strong to be able to form a hydrogen bond to a neighboring water molecule, to a lone pair. There's a lone pair on a water molecule. Now oxygen has actually got 2 lone pairs, and that's quite important there. Okay, so you can get hydrogen bonds in water. Now, why has water got a considerably higher boiling point than HF? I'm not entirely sure whether you'd have to mention this for the look at the mark scheme, but the reason why water's is much higher is because in H2O you have got 2 partial positive hydrogens, and you've got 2 lone pairs on the oxygen. So that means on average each water molecule can form 4 H bonds. Whereas if you look at hydrogen fluoride, right, hydrogen fluoride, you have got 3 lone pairs on the fluorine. So you may think that, well, they can form 3 hydrogen bonds, but they can't, because you've only got 1 hydrogen. So on average, each HF molecule is only going to form 2 H bonds. There's basically a lack of hydrogens with a partial positive charge, and you've got too many lone pairs on the fluorines, so you only get 2 H bonds per molecule. That explains the difference in the boiling point between HF and water. Now, the most obvious thing we need to talk about now is the methane. That has got a way lower boiling point than the other 2. Now, if you look at the electronegativity between hydrogen 2.1 and carbon 2.5, it's actually very small, and so there's no with methane there's no partial, or you may get a very slight partial charge on the hydrogens because they are ever so slightly less electronegative than the carbon, 2.1 compared to 2.5. But importantly, this is also a symmetrical molecule. It's a tetrahedron, so there's no permanent dipole, even if you did have a difference in electronegativity, and there is very little difference in electronegativity. No permanent dipole, so you can't get hydrogen bonds, obviously. You can't get dipole-dipole interactions. So the only kind of intermolecular forces that you can get are London forces. And that, of course, is the attraction between a temporary dipole on one molecule and an induced dipole on the neighboring molecule. London forces are the weakest kind of intermolecular force, and so that is why you have a low boiling point for methane. Okay, question 8 is about ionic bonding. Sodium and fluorine react together to form an ionic compound. Select the correct equation for the reaction. Well, let's just think about this. Sodium is in group 1, so it's going to form a single positive. Fluorine is in group 7, so that's going to form an F minus, gain 1 electron. So the formula of the compound is going to be NaF. And we also have to remember that the halogens all exist as diatomic molecules. And so the one that we want is this one. Let's see here. Well, that's wrong because the fluorines are not diatomic. That's right. Okay. That one is wrong because it's the wrong formula for sodium fluoride, and that's a wrong formula. So B is the right answer. And 2, draw a dot cross diagram of the ions in sodium fluoride showing all the electrons, and use your diagram to explain why the ions are described as isoelectronic. So we look at so fluorine is atomic number 9, so it's going to have 2 in the first shell and 7 in the second shell. So the fluoride ion is going to gain 1, that's going to be 2, and then 8 in the second shell. We look at sodium, that's 11, so it's going to be 2, 8, 1. Sodium is going to lose 1 electron, it's going to form a single positive ion, 2, 8. Now you forgive me if I don't draw a dot cross diagram. Well, I suppose I'll draw it. So let's show the fluorine here. Right, so we've got 2 in the first shell. We've got 7 of its own electrons, and then a dot which is got from the sodium. Okay, put a minus there. And here's Na. 2 in the first shell and 8 in the second shell. And a single positive charge up there. Okay. Why are they described as isoelectronic? Iso means the same. They've got the same electronic structures. They've got 2 in the first shell and 8 in the second shell. Or if you wanted to say in SPD notation, we want the both 1s2, 2s2, 2p6, both of them. Okay, the same electronic structure. Right, which diagram shows the trend in ionic radius for the isoelectronic ions N3 to Al3+? So they've all got this. They've all got the same structure of isoelectronic structure there. Right, I'm just going to write down that bit of the periodic table. So we've got nitrogen, group 5, oxygen, fluorine, neon, group 5, group 6, group 7, group 8. And that's going to be atomic number 7, 8, 9, 10. And then, of course, we start a new row. We've got sodium is in group 1. It's got 11, atomic number 11. Group 2, we've got magnesium, 12, and 3. We've got aluminium there. Okay. Now, you can see that as you go across, the number of protons increases. So even though they've got the same electronic structure, the attraction of the nucleus on those electrons gets stronger. So that means the atomic radius is going to decrease. And it will decrease in a fairly linear sort of way. So let's have a look. Which one is it going to be? Well, the ionic radius, the biggest one is the nitride ion because that's got the smallest charge. So this is the right one. A is correct. Okay, so you get just a trend going down like that. This one, the trend is in completely off the wrong way round. This is the trends in the wrong way round. And here you don't get this discontinuous thing going on there. Okay, it's A is the right answer. Right, explain your answer to A3 in terms of the structure of the ions. Well, I think you need to say, I've explained it really already. Same electronic structure, but nuclear charge increases. Okay, the strength of ionic bonding in different compounds can be compared by using the amount of energy required to separate the ions. Some values for the energy are given in this table. Okay, so for lithium fluoride, potassium fluoride, and calcium fluoride, using the data provided, explain how changes in the cation, so the cation is the positive charge, the metal ion, affect the bond strength of an ionic compound. Right, now why is calcium Why does that require more energy to separate out calcium fluoride? Well, of course, calcium is in group 2, so calcium forms a 2+ ion, whereas lithium and potassium are both in group 1, so they only form a 1+ ion. So obviously the electrostatic attraction between the calcium ions and the negative fluoride ion is going to be a lot stronger because this is 2+. Now we need to explain why the difference between lithium and potassium. Well, if we think about the size of these ions, you're going down group 1, so lithium is going to be the smallest, and then sodium's not mentioned, but that will be the next one down, and potassium is going to be bigger still. Okay, right, so you can see as the positive ion gets bigger, its charge density is less great. So you've got the same positive ion but spread over a much larger volume. Okay, so it's lower charge density. And that means the attraction for the negative fluoride ion is going to be weaker. Another way of looking at it is to say that the separation of the potassium ion and the fluoride ion, so the separation for them, between the middle of that ion and the middle of that one, is going to be bigger. So the charges are further away, so the attraction is less great. Or you can explain it in terms of charge density. That is the end of that paper.